All right, so the questions about the test. So the test, I'm not yet sure. So the test is going to be conducted online. This is pretty certain. It's very unlikely that we will have any kind of directive to do it otherwise, for different reasons. The thing is, so even if right, okay, despite the recent certain easings, that if you okay, yeah, so so despite the recent relaxing of lockdown conditions, it's very unlikely that we're going to have any kind of classes this semester, and in particular, it's very unlikely that we're going to write tests. So therefore, even if you go somewhere, you can still do it online. Well, it may be inconvenient time zone for you, a little bit inconvenient. But apart from that, I see no obstacles as long as you have internet connection. Right. So I'm not sure what the test, what platform the test is going to be. So I have looked a little bit, but I haven't found anything particularly satisfying, because so I found some commercial options, but okay, they're commercial, so I'm not sure about them. And then I found some, and then some universities have something for their own students or for their own kind of staff, but this is also, I'm not sure that our university has it. So it's one option that seems to be plausible, that is just going to be some kind of Google questionnaire or something like this. Of course, with you will have to write for example, the number as an answer, or the function as an answer, and yeah. And of course, so most likely the tests are going to contain, so the problems are going to be kind of personalized by having your by having your by having your student number being part of the task. So what is somebody's writing me that I can conduct the test as MCQ, but I'm not sure what it is. Multiple choice question. Yes, something like this. This is going to be something like this. Or so either multiple choice questions, or you just you have to write an answer, right? So just an answer. Of course, I understand that technically, well, it is possible, of course, to do kind of to write and make a picture, so it's not so difficult. But to do it for everybody, and then maybe somebody has a problem with it. Maybe somebody don't have a camera which could do it. So I think it's better. Yeah, it's better to do it like this. Yeah, so we're going to have either multiple choice. I mean, so some task maybe multiple choice, or maybe just that you write an answer into the field, right? So this is going to be an idea, and then the question is going to contain at least some questions are going to contain some elements of your student number, right? So that it's personalized for each student in this way. But you will have also enough time for the questions, because of course there is no it's not like we have a room that we need to vacate, right? So yeah, so you will have enough time, more time that usually would be assigned for such a test, definitely. So that of course you can have you will have an option, and of course even at my normal, I prefer, even at normal tests, so conducted in under normal circumstances, I allow the students to use everything, except of course communicating with each other. So of course, here you will also be able to use every source. Now, of course, I would like to prevent you from communicating from each other, but of course I cannot do it. So it's so it's I cannot do it. But of course, you will have personalized tasks. So it will take. This is where you cannot just for example get the answer by email or so by chat or something. You would need to this creates some additional, I think, natural obstacles for let's say this kind of cheating with communication. So I would encourage you to do it, of course, on your own, and especially because you have you can use every resource available to you. Like you can use all the things that you can use the entire internet, right, at your disposal. Okay. Okay, so with this out of the way, let's now move on to the integrals. So you remember last time we talked about them, and so we discussed how to take them. So the integral is an inverse of the derivative, right? I should share my screen. So integral is the inverse of the derivative. Okay, so let me. Right, so okay, so you also have the definition of antiderivative or antiderivative. So, and this is pretty similar to the integral, but remember that so somehow an antiderivative is a function, right? It is a function, so it's a specific function, while the integral is a little bit a looser kind of notion that it represents here a collection of functions, but it can also be just represent an operation or a symbol. So the integral is kind of it's a little bit loose, a looser, so notion, a little bit wider, right? But okay, so it's not wrong to say that the integral is a collection of functions which are given by this expression, right? And then antiderivative is a single function. Okay, so and then we discuss how to take them. So how to compute the integral. So, and of course we start with indefinite integral. And remember that indefinite integrals, you have no limits here, right? So we also discussed yesterday definite integrals, and we're going to also kind of revisit them today. But those are the indefinite integrals, and so, which have no limits. It's just the integral sign, and that's it. Okay, so and those are the basic rules, so that the additivity and the minus goes away, and the sum and the differences, right? So that you can, so the integral is additive, and so on. Okay, just like derivative, the derivative operation, the integral is not multiplicative. So this is wrong. I mean, so this is not equal to this. So I mean that if it was equality here, it would be wrong. And respectively, this is also not true, right? So this equality, so this inequality holds that it is not an equality, right? So this is This is just important to keep in mind, not to make such a mistake, right? Okay, and then to compute the integral, so you try to reduce it to the right. Okay, so one way is to use the table integral. So let's say we call it a table integral. If you have a function under the sign of integral, for example, this one, right? Okay, you can split. This is the sum, right? So you can split it into 3, and then if you look at each function, you recognize that it looks like a derivative from a table, right? So you remember that. So you remember the derivatives of polynomial functions, of some trigonometric, of logarithm, of exponential function, right? And those, so you remember those derivatives, but then you can inverse, right? So if you remember the result, then you kind of can find out what was the function which was being differentiated. And the integral is an inverse operation. It is the inverse operation to differentiation, right? So inverse to the derivative. So for example, if you have here x to minus 5, then you remember that you need to take x to minus 4 times something to get this, right? So x to minus, because if you take a polynomial, then you reduce the exponent by 1, right? So it is minus 4, and then you reduce by 1, you get minus 5. So you have to get this. So you write x to minus 4, and then you check that the coefficient here. So the coefficient here is 7, right? So if you just take 1 x minus 4, you're going to take minus 1/4, right? By the derivative differentiation rules is going to be minus 1/4 x to minus 5. And so you also multiply it by, minus 4, I should say. No, not minus 1/4. It's going to be, if you take the derivative of x to minus 4, it's going to be minus 4 times x to minus 5, right? But and you have to, you need here plus 7. So you multiply by minus 7/4, right? So you adjust this coefficient so that you get the right coefficient also here. Okay, and this is how you do it everywhere, right? So this is kind of the basic technique. Okay. Okay, so and then of course sometimes you have to do some transformations to get this to the required format. For example, here you have this product which you don't know how to integrate directly, but then you recall this formula, right? And then you apply it here, and so you get this. And so this integral equals to this integral, but this already you know how to integrate, right? Because this is sine is the derivative of minus cosine, right? And so you get this. Okay, and then also you have so if you have the derivative and a value, you can uniquely determine your function, right? So you have this formula, right? So okay, so this is, by the way, what it means for that the integral is inverse to the derivative, right? So this is, so you have f on the left hand side, and on the right hand side you have integral of the derivative of f, right? So they kind of cancel each other out and result in f. Of course, here there need to be a caveat that you remember that this is defined up to integration constant, which is of course, right? So you have to keep that in mind, that of course you cannot have one function to be equal to the class of functions. But this is still how you can treat it, right? Having this in mind. And so you have this function f prime, and you find the derivative of it. So you integrate, right? So you integrate each term and you get the derivative, and that's fine. And then, okay, so you have this integration constant. And then you're given that f of 0 is 15, right? F of 0 is 15. So you just consider it as an equation, right, with respect to c, and you get c equals to 10. All right. Okay, so and then one of the main tools of how to compute the indefinite integral is via the substitution. Okay, so for example, okay, so this is the first example. So this is not an example that you can just look at the table and come up with a function which would give you this result, right? But what you can do, you can notice that if you take this function in under the root, right, of degree 4. So if you take this function and differentiate, you are going to obtain this kind of x squared times something, right? So so and this should hint you that you can use a substitution technique. So you take u equals to this expression, right? And then the derivative of u is going to be this, so the differential. And so you can write it like this, right? And then you find this integral in terms of u. And then you just, and then not to forget, at the end, so please do not forget at the end to come back to the original variable, right? Never forget the original variable. Okay. Okay, so and this is in an abstract form, right? So that you look for a certain function g, so whose derivative you have here as a product. So for example, here in this example, right, it was this function whose derivative we also have here. So for example, in this example, right, in the you see that the derivative of this polynomial inside inside the parentheses is going to be something. So it's going to be something similar to this thing, maybe proportional. So this polynomial could be our substitution. Okay? In this example, you have once again w minus logarithm of w. If you differentiate this, you're going to get exactly this, right? Exactly this expression in these parentheses. So it's going to be 1 minus 1 over w. So you can have new variable as, for example, u equals to w minus logarithm of w, right? That can be your new variable. And in this example, finally, you can take this expression in the exponent as a new variable, right? Because if you take the derivative, the derivative is going to be 8y minus 1, exactly this thing here, right? So you can take as new variable this. So, and then, of course, the art is to learn to see that from the integral, right? So Okay, so I think you had in the homework, you had many examples of that, right? So this is just something to be aware. Right, and then, for example, in this integral, for example, you need to first split integral into two, right? So you split into two, and then this one is a table integral. Remember, this is Arcus tangent, this one. Okay, so this one you kind of, this one is covered. And then for this integral, right, for this integral, you have this x squared plus 1. The derivative of x squared plus 1 is going to be exactly x, exactly this one, or 2x. Okay, so you need to put 1/2 also here. And so you can compute this integral like this, right? And then you proceed from here. All right, so okay, so this one also is an interesting case. So this is actually not obvious what to do here at the beginning, right? But then you can remember that if the derivative of square root is going to be 1 over square root, right? Times 1/2, right? But this is by the formula. So so this is in fact just if you take the substitution, it's all going to connect, right? And so it's going to work. So, but of course, at the beginning it's not obvious, but this is you can interpret as a multiplier of 1 over square root times dx, and then you can see that okay, the square root substitution does work. Yeah, I think this example we did consider last time, right? Okay, so and this is a difficult, I think, a more difficult example. So let's so we should discuss, I think, one problem also just like with like this in a more slow at a slower pace, right? 2x cubed square root of x squared plus 1, right? So it's going to be 2x cubed dx, right? 2x cubed, so I hope that's correct, yeah. Okay, so what to do here? Okay, so for example, if it was 4 here, right? So if here we had like 4 instead of 2, then you would say, okay, this is pretty, I mean, this is clear how to do. You take this as a new variable, right? U equals to x to 4 plus 1. The derivative is then something times x cubed. So, and this is what you want to get, this is what you have. But this is not what we have. So we have here x to x squared, and here we have x cubed. So this doesn't quite work out. But we can, let us rewrite it like this. So I'm going to rewrite it if I manage to do it. right? Okay, and here of course we have multiplier. Okay, so what I did, I didn't change the expression because I just wrote, I represented x cubed as x times x squared. Right? Okay, so what is going on here? So now we have, this is an expression of x squared, and this is something, so here x squared, and then here we have 2x, and the derivative of x squared is 2x, right? So we now make a substitution, and once again, we can do it on the fly, right? Okay, so I just write here u equals to x squared, du equals to 2x dx. So we do this on the fly, and then we get, what do we get? So we get u times square root of u plus 1 du, right? So this and this gives us du, and then the rest remains, right? All right, so this looks a little bit simpler, but still not quite clear how to take it. All right, so still not clear how to take it. So what we do here, we can take another substitute. So let us try. So this is on a table integral, right? So we have here square root. So let us try t equals to the square root. Okay, so we're doing another substitute. Okay, so then we need to express u via t, right? So it means that t squared is going to be u plus 1. So you have, right? And so, okay, so now we can compute. So first of all, u equals to t squared minus 1. And second, that du is going to be 2t, right? So in this way, we get rid of irrationality here. So this is going to be then, so u is t squared minus 1. This is t, right, times t. And then du equals to 2t dt, right? We must not forget dt here, right? So 2t dt. All right, so, and this is something that we already can integrate, right? This is just going to be a polynomial, right? So this is going to be 2 t to 4th minus t squared dt. Okay, so in this we can integrate. So we can integrate this, and yeah, so this is going to be 2/5 t to 5 minus 2/3 t cubed. plus constant c. Okay, so and we made two substitutions along the way. So we gradually reverse them. The first one, remember what was t, right? So it's going to be 2/5 square. Okay, so it's better to write. So square root is power 1/2, right? So I can write like this: 5 second minus 2/3 u plus 1 at the power 3 second. And then I come back to this substitution, right? So I just replace u with x squared, right? Okay, 2/5 x squared plus 1 to the power of 5 second. And plus the constant, of course. All right. So do you have some questions regarding this example? All right. So let's see. So of course, right. So a smarter way, actually, well, a smarter way to do is directly. You see, we did a substitution x squared, right? And this is maybe what is kind of asking, right? So this is what you want to do because you see this and you want to do u equals x squared substitution. But of course you can combine. So but we have ended up having to do two substitution. Remember, this is how you can read. You can integrate square root. You can just, if you have square root, then you just take a new substitution, and this works out, right? Okay, so of course you could, but if you take this substitution directly plus 1, then of course it's you just need to do only one substitution. Okay, so okay. Okay, so and let's just discuss these integrals are all of the same type somehow. For this, so this is not 1 over sine, but this is the arc sine, right? In this text, in this manuscript, this is arc sine, arcus sine, sine, and uh, uh, and this is the derivative of this, right? This is a derivative of arcus arcus sine. So this is, once again, this is of the same form, and here you get the substitution, right? Okay, so just 20, give me 20 seconds, okay? All right. Okay, then we discussed how integrals are related to the areas, right? Okay, so this we're going to skip now. And then we discussed what is a definite integral, right? So this is a definite integral. This is how it is defined, but the definition is never used, practically never. So this is an integral where you have also limits of integration, right? A and B. So you have limits of integration, and this makes integral definite. Okay, so then you have the basic rules once again the same. So this is one important that if you change the limits of integration, it's going to be the minus, right? The minus comes up. Then this is important to remember. And then of course the additivity if you add a new number. So those are important to remember. Okay, so but then computing the integral is there are a couple of tricks, but pretty much it's the same. That but most of the time, what you do is you compute indefinite integral, and then just okay, yeah, well, and then use this this fact, right? The fundamental theorem of calculus. Or like this, right? So this is more. This is the standard form that you can also use. So you compute it in this form and then use it the fundamental theorem of calculus. Okay, so there are exceptions to that. So for example, if the function is odd, then you can, and the integral is, the interval of integration is symmetric, for example, from -3 to 3 or -6 to 6, then you can just say that the integral is 0, as long as it is defined, it is 0, right? So if the function is continuous everywhere, then it is 0. Right. Okay, so and then the computation of definite integrals comes down to the computation of indefinite integral, right? So this is definite integral. So you take the antiderivative, and then it's just the computation, right, of the values. You remember. Okay. Okay, and then let us also discuss a separate rule for the substitution rule for definite integrals. So as we also discussed last time, there are two ways you can apply the substitution rule for definite integrals. First, you can just so you can just try to compute the indefinite integral by the substitution rule, right? So you just compute the indefinite integral, and then after you compute indefinite integral, you come back to the definite integral. The second method is a little bit shorter in that you change the limits of integration, right? Because remember, if you do the substitution, you also need to change the limits of integration. So don't write like this, because this is a little bit confusing, because if you write it like this, it is strictly speaking not correct, because this reads as integral. This is not the same as this thing, right? Because if you make a substitution, then your values are going to change. So you want your values to change also here. So this is how you can you do it, right? So you recompute the limits of integration, and then you substitute. And so please note, for example, here Okay, so those are the limits of integration. And then you can proceed, right? Usually you want somehow the higher value to be on top. So, and for that you would need to change the sign, right? You remember, but of course, formally it's not needed, not necessary. But this is how it's common to think about it. But of course, if you are comfortable with higher number being on the bottom, that's up to you. So that's totally fine. Okay, and that was kind of the main point about the change of variables. And apart from that, it's very similar, right? So but you need to recompute each time the new limits. So this is a new aspect for the definite integrals. Okay, so, and then with this, we more or less covered, I think, what we covered last time. And so today we're going to discuss a little bit more, a little bit about the area problems, and then we're going to discuss two more methods of taking the integrals, right? Which were not discussed here. Okay, so but now let's have a pause. Let's have 10 minutes break. Okay. Or let's have maybe 5-minute break. Okay, so then we're going to cover this thing here. Then we're going to have another break, and then we're going to cover two more methods, and that's it. Okay, so 5 minutes or 5-minute break.
Unfortunately, I didn't get my keys.
Oh, I didn't receive a
Oh,
call
that's okay.
actually.
Oh, that's okay. It's okay
Yeah.
because I was like about here. Whatever. How did it go?
Okay, so the differential integrals can be used to compute various things related to area and volume. So the classical example is okay, the average value of the function. This is not very interesting. The classical example is the area is for the area. For example, the area between curves. Now, if you know that one function is strictly larger than the other, then the other, then the area between those two curves is given by this integral, right? So of course, this is also true if you change your independent variable, right? So this is basically turned by 90 degrees. Now, if you want to compute, if you want to compute area between such two functions, what you need to do, you need to split into the intervals where one function is larger than the other. And then you can still do it as I do here. You see, so that okay, you have integral from -2 to -1. Okay, this is one thing. Right. Okay. But you need to check this this function with plus sign on this interval, and this function with minus sign on this interval, right? The blue comes with minus on the first one. So the blue is this one, so it comes with minus. Then from -1 to 3, it's reversed. This function, the line comes with plus, while the second function comes with minus. And then from 3 to 5, it's once again as originally, the red function comes on top with plus. While the blue function comes with minus. Okay. Okay, so this is just important to be aware of. This is not too difficult, but this is something to be aware of. Now, a more difficult kind of problem, which we will not go into detail, we just discuss it. You can actually compute also volume of revolving bodies. So that if you have a body which can be obtained by moving a two-dimensional thing, two-dimensional shape around an axis. So imagine that you have, okay, you have this picture, right? You have this picture, and then you move. So you have this two-dimensional thing in your real life, in your hands, and then you move. You fix this axis x axis, and then you move the entire thing around this fixed axis, right? With x fixed, right? So that imagine that you have, okay, I can actually maybe show. Okay. So imagine that this is my figure. Okay, let me take something nice. Okay. Okay, so imagine that this is my figure is also my phone is my shape, and then I fix the position of this axis, which is given by my pen, and then I start moving, right? And then I move around the axis. So this is how I move it, and then my phone kind of moves around. So I then take a three-dimensional object, which is given by all the positions of my phone at different points, right? So I can move all around, and so right? And so this is what we also see here in this example, for example, right? So you take this shape and then you move it around, and this is what you get at the end. So, okay. So how to compute the volume? So you can compute the volume, in fact, with the integral calculus. Right. Okay, so to do it, so I'm just looking for the formula. No, okay, so to compute the volume, what you do is so you take this height function somehow, right? So okay, so let's consider an example. So okay, so you have this function, right? Okay, so then you imagine how it looks like. So okay, so in this example, you rotate y-axis around around itself, right? So okay, so let's look, for example, where you rotate just x, because it's a little bit easier, right? So okay, so you have this function. So this is your function, right? So at each step, you somehow have this circle, right? So because right, so of course, if you have also my phone, if you imagine it rotating, at each point, then if you take one cross section like this, right? So you have a cross section of this plane, like my palm, then it's going to be a circle as intersection, right? And you can see it also here on this picture. Okay, so and then what you can do? So you can find the radius of the circle. Okay, so you find the radius of the circle. for each x, right? So okay, this is now a function of x, and okay, so you find the radius, and then if you integrate this radius, this is going to get to have your volume, right? So you find for each x, you find the area, the two-dimensional area of the respective intersection, and then you integrate. And this is how you can find the volumes of spinning bodies. So, for example, yeah, this is so A of x is the area of the circle, right? And that is the same if the body revolves around y-axis, right? So it's just going to be different. So here you have you see you have an annulus or a ring. Now, how to find an area of the ring? You take the area of somehow the largest circle, subtract the area enclosed by the closest smaller circle, right? So this is okay. Okay, so but this is just for information, so this we will not go deeply to. Okay, and then of course, okay, so we have discussed the areas, right? So the area, for the area, you also have the same principle, and we have also just discussed it tangibly, right? Oh, that's really fun. Okay, so then let us now have another break, and then we at the end are going to discuss two more rules about the how to take two more techniques, how to take integrals, and then we're going to finish, right, for today, and finish. I mean, for the entire course with the new material, right? Okay. Right. So let's have a pause and see you in some minutes. In 10 minutes, let's say. Okay. Okay, so then two more techniques to compute integrals. Now, if you have an integrals of such a type, for example, you have x squared square root 2x plus 3. Okay, so how can you compute it? So if you have this kind of integral where you have this here a polynomial times square root, what you can do is you can take the new variable. You can take the following type of this type of substitution. So you take the square root as a new variable, right? Okay, so then what you get? You get t squared equals 2x plus 3. So x equals to 1/2 t squared minus 3 second. And dx equals to, okay, and so it's going to be t dt, right? Just t dt. And so with this substitution, you reduce such an integral to an integral of a polynomial, right? So x equals to this. So x squared is going to be 1/2 t squared minus 3 second squared. That was x squared. Then we have t, right? Because this is t. And then dx is t dt. So it's going to be t squared dt, right? Okay, so in this one, you can just open the parentheses and so okay, so it's going to be 1/4. So I put away one half here. So it's going to be t squared minus 3 squared. So it's going to be t to 4th minus 6 t squared plus 9 t squared dt, right? And then I can now, okay, so that's going to be t to 6. So the integral is going to be 1/7 t to 7, then so it's going to be 128 t to 7. So this is t to 4th, 150 to 5. So it's going to be minus 6. So minus 3/10 t to 5, right? And so on, right? And plus 9g squared, so it's going to be 3/4 g cubed, right? I think that's fine. Hopefully this is correct. So and then you just return to the previous variable. So it's 128 2x plus 3 to the power 7th second. Okay, and by the way, of course here plus c, right? We do not forget plus c. Okay, and so on, right? So I hope so this is one. So this is not covered in this book. So please remember it. The important technique. If you just have one square root, you introduce new variable by denoting square root to be this new variable, right? And that's it. So it's not difficult, but please remember this trick. Okay, and then another one is the integration by part. So consider this integral. Now, what is integration by parts? By parts. So the formula is basically as like this: f g dx equals to no, sorry, this is wrong. So the formula is like this. So I need to. Okay, so this is schematically, of course. So what is here? So here small f and g are small function, are certain functions, and capital letters are their antiderivatives, right? Okay, so but let's see how it comes into play, because this is one thing to see the formula, and another way to see how it comes into play. So this is a classical example. Okay, so you have this integral. So it's not a table integral. So how do you compute it? So you write it like this. So it's going to be x, and then you can write it like this, dEx, right? So this is exactly this, right? And then you apply this formula. So it's going to be, okay, so you have something times d in other function, right? First function times d second function. So you take their product here without any integrals, right? Without any integrals, and then subtract the second function times d, the first function. And in this case, the first function is just x, so it's going to be just dx. And so you get x ex minus ex, right? Plus c. Right? So let's say another example is if you take this integral sine x ex dx. This is a little bit more complex. So, okay, how can you compute it? You write it like this. Okay, right, that's fine. Okay, then you write. Okay, so you have one function times d another function, right? So the integral. So you take the product of two functions minus this function times d this function minus e to x d sine x, right? Okay, I continue. Sine x ex. Okay, the differential of sine is cosine, right? Minus integral cosine of x ex dx. Okay, this doesn't give us anything yet because now we reduced to this integral, so it's not clear if we made any progress. But let us continue. So this is once again is going to be dEx, right? So we once again apply this formula. So it's once again, so sine x ex. So this is a product, right? So it's a little bit. Minus cosine. No, this is not. Minus cosine of x ex, right? Plus integral ex d cosine of x. Okay. Okay, so then so let us see what comes up out of this one. Okay, so sine x ex minus cosine x ex. That's fine. That's the same. Okay, and then we have here ex d cosine x, right? So d cosine x is going to be, by the way, first of all, we have here plus, right? Because here we had minus, and then in the formula we also have minus, so we have here plus. And then here we have minus, right? Because d cosine x is going to be minus sign, so it's going to be ex sine x dx. Okay. Okay, so let us see what was going on. So we started from here, right? And then we had this thing again here. So what is going on? So it's not clear if we made any progress at first, but in fact we did, because so denote this thing by I, right? So this is I. Then we know that I equals to ex sine x minus cosine x minus I, right? And so from here we get 2I equals to this expression, right? Or we can just write that immediately. I equals to 1/2 ex sine x minus cosine x, right? And then, okay, of course, we need to add the constant because you see, so we have a constant somehow here, but also here we have an integral, so we need to add a constant because and that's it, right? So we have computed this integral, right? So okay. So, and with this, we are going to finish for today. And especially for the new material for the course. So if you have some questions, you can ask. You can ask now, of course. Okay, so about the tests, let me also say that, of course, we are going to have multiple tries. That is definitely the case. Of course, you want to do it as early as possible so that not to be bothered later. Okay, so I think I told you, I have told you already a little bit about how it's going to be, but at least from how I envision it. Of course, I still myself, so I'm not 100% sure about the platform, but probably it's going to be just something very simple, maybe just a cool questionnaire, this stuff. Yeah, so okay, so I have sent I have sent I think multiple times to you this manuscript which I recommend, and basically everything that we covered is in this manuscript, except what we just covered right now about the integration by parts and this substitution for square root. You remember? Just 20 minutes ago, let's say. Okay, so and with this, let us finish for today. Okay, so thank you for following. So if you have some,
yeah,
yes?
I'm sorry. On the test, will it be only solving problems or theory too?
It will be yeah, it will be only problems.
Okay, thanks.
Because you have to know some theory, right, to solve them, but we didn't really have much theory anyway. Let's say properly, most of it was computations and just the techniques to learn. So yeah, it's going to be mostly the problems, only the problems. Okay, so if you have some other questions, you can still ask within the next 10 minutes. And then if not, then we're going to finish as usually. I'm just going to end the meeting, right? And so preliminary, bye.
Thanks, goodbye.
Well, the homework, of course, I don't know. It's supposed to be the kind of each time you do the homework. So I'm going to check the homeworks. I have a backlog of homeworks which I haven't checked yet. I did check some of them. So they're going to be as bonus points. If you do well the homework, then you will get a little bit of bonus points. But you can consider them as a practice for yourself, because the types of problems on the test, so the problems on the test are going to be of exactly the same types or as our homework problems, right? So so I would suggest you anyway to even you have done it, just to review it, just to review how you did it before the test. That's fine. Of course, you will also have time during the test to have a look at the homeworks, right? But of course, it's just if you just review it a bit before the test, then maybe it's going to be a little bit easier during the test. Okay. All right, so when the test is going to be, so I think most likely, maybe in a week or maybe in 2 weeks. All right. So yeah, it depends because I'm not sure. I haven't done it, so I don't know how to set it up. Everything I have to set everything up that everything is smooth and right. So I'm just not sure what it takes yet. So I cannot tell you. But yeah, so let's say if I don't tell you by Wednesday that it is going to be next week, right? So if it's not, it's I'm not telling you by, it's I'm not if I don't tell you by Wednesday, then it's going to be not next week, but the week after. So how many problems will there be on the test? I'm sure. So it depends a little bit on what kind of problems there will be, like the difficulty, but you can expect some problems from every, like for the limits, right? For the limits, or like maybe 3 to 4. Then for the derivatives, maybe 3 to 4, and for integrals 3 to 4. So in total, up to 15, a little bit less than 15 probably, yeah. And of course, but you will have time to do it. Maybe a little bit fewer than 15, maybe, right? But there will be time to do it. So you will have time to do it, definitely. Of course, some of the problems will be very short, right? So then some of those will require some substitution or L'Hopital rule or something. Yeah. Okay. I hope that answers the question.